Okay, I'm back and I'm badder than ever. Okay, and apparently my camera has reset, and this is going to be a whole new video for chapter 24. So, our design step number 4 is design details. Let me recommend that you read through chapter 24. Like all the chapters in this book, it's pretty short and easy, but it gives a lot more examples of how to design than are in this presentation. Okay, what you will learn. I hate those slides. All right, so in detailed design, we want to analyze our design. As much as possible, we want mathematical models that tell us, yes, we're going the right way, or, oh my God, what were you thinking? We might want to do experiments with models of our parts or parts of our concepts that we feel like maybe that's a little bit shaky. We don't know how well that's going to work. And then we want to create detailed drawings. So look for a program online that will let you do drawings. There should be some, and look for one that's very simple. I mean, don't download a trial version of AutoCAD. That's way too complex to use. In fact, ordinarily, when we teach people to use that, it's a class that takes a whole semester. But there are some programs that are easier to use. I am partial to Visio, although, now that I think about it, I don't even know if Microsoft still supports that or not. But my point is there are other things available. For that matter, I once did a design using the Paint program on the computer of a concept that they, for the Corpus Christi Army Depot, that they are still using there. All right, so they're talking about using analysis of mathematically. So we have a boat which has a material thickness of 0.10 meters. In other words, 10 centimeters. The thermal conductivity is 1.50 watts per meter degrees centigrade. So when we look at how fast heat transfers, we look at the material conductivity, and it is going to be how much heat can pass through per the thickness and the difference in temperature. There's a power source on board that is producing 150 watts per meter squared of heat. 150 watts per meter squared. That seems like a suspicious way to measure the amount of heat produced, but I'm going to go with it. The surrounding water is 20 degrees centigrade. The boat material can't exceed 100 degrees centigrade. In other words, 100 degrees centigrade would be at the boiling point. Now, do we want to risk operating our design without knowing what the maximum temperature is going to be? Okay. All right. So Fourier's law of heat conduction is that heat transfer, Q, equals K times the difference in temperature times the thickness of material. K is the conductivity value that I discussed in such length before. All right, so they rearranged the equation to make it the temperature of the surface is equal to the temperature of the water plus heat transfer times the thickness of the material divided by the conductivity of the material. Temperature of the water is 20 degrees C. So our heat transfer is 150 watts per meter squared times the thickness of material, or 0.10 divided by 150, so that's watts per meter squared times meters times square meters degrees centigrade divided by watts. And we end up with an estimate that it's going to be 30 degrees centigrade in our machine, whatever it is. All right, well, they say the material is going to not be any good at 100 degrees. We're at 30 degrees. Bob's your uncle. We are there. All right. As I said before, sometimes we want to do experiments just to make sure we're on the right lines. So when we do that, we're going to make a crude model or prototype and check and see if we've got the bugs out, or if we need to go back to the drawing board, or if we can tweak our design, whatever. So they have the dueling duffers device, and the idea is it's supposed to go over and deposit balls on a board against an opposing team. Okay, man, whatever. So they're using a 2-liter bottle where they've removed the top. The bottle is going to pivot around a steel rod. So it looks more to me like they've cut the bottom off the 2-liter bottle, right? So then over here, they've just made an approximation of that as quickly as possible to see what they need to do, whether that is something that's going to work, or can we tweak it and it will work, or this is just a totally useless design. We need to start over. All right. So what experiments will help? Anytime there's a risk that it won't work or uncertainty about whether it will work. So in the case of the dueling duffers, they want to know, will all 10 balls fit in the top half of the 2-liter bottle? Okay. What on top of that, they ask, what is our optimum height to dump the balls? Will all 10 balls drop into the hole when dumped in this manner? Okay, well, guys, you're bringing up something you didn't bring up before. That when it drops on the opponent's board, it's got to go into a hole. Is it important to have the vehicle perfectly positioned before dumping the balls? Will the machine travel slowly enough that its position can be easily controlled? Right? So sometimes we want things to go very fast, sometimes slow. All right. So, ordinarily, our engineering drawings are not hand-drawn unless we draw them extremely neatly. Of course, I went to engineering school in the era when the very first CAD programs were starting to come out. So we learned totally to draw everything by hand and be extremely neat. You want to draw to scale and have at least 2 views. You'll notice here we've got a side view and a front view. Sometimes you need all 3 views, front, side, and top view. So you want to make sure that you have enough views, though, that anyone looking at your design understands what it is and what it does to be able to evaluate it. All right. So we show hidden lines. In other words, if you have a hole through something but you're looking at the side, we portray that with dashes. We only show as many dimensions as we need, and make sure that you remember when we went through about drawing that a lot of times you'd say, hey, wait a minute, there's no dimension here. But when there's no dimension, you should be able to infer what that dimension is by adding up or subtracting some of the other numbers. Always notes and labels as much as possible. If you don't necessarily know how to manufacture, don't worry about it. Show the concept. And if you're going to use an electric circuit, show it as a circuit diagram. One of the reasons I like Visio is it will actually let you draw circuit diagrams, regular engineering drawings, or architectural drawings, not to mention flow charts and some other things. All right. So I'm going to say this is not your assignment. Let's move on. Now, that is not to say that I don't want you all to create good drawings of your concept for your project that will show exactly how you would do it, or at least the outline of how that would come together. All right. All right, so our Chapter 24 summary: use numerical answers where that is possible. I am confident you can look online and find answers to how well your design would work. We want models on things that we don't know about, we aren't certain about, and then we want a good, solid design. And always we want to document what we have done. All right, so let me look here online. Oh, bloody hell. I had no idea I had so many things open. All right, and all right, there we go. Oh, hey, the video I started uploading yesterday has finally loaded. Hurrah! But what I want here is Bernoulli's principal equations. And it's thinking about it. Okay, we're getting closer every second. All right, so you can see here, I've got the Wikipedia article. That's obviously going to be the easiest one to get. I'll click on that. And come down here. All right. All right, so I get some different ideas here of possible possible equations. Right, you'll notice, what is Q? Oh, okay. So Q is, in this particular one, is dynamic pressure. At the speeds we're going to be talking about looking at your airfoils, that's not going to make any difference. We could call that zero. Rho here is the density of air. G is gravitational force or acceleration, and H is it says here piezometric head or hydraulic head. All right, well, I've got my doubts about how high that is going to be, and that is going to have some difference because we're in the mountains. So possibly we're going to need to go to this equation. Anyway, feel free to read through some stuff about Bernoulli's principle and figure out what you would think the lift is going to be. Anyway, all right, so that concludes our Chapter 24 presentation. I am going to upload these to YouTube, and good luck to me. Please stay safe, keep social distancing, keep self-isolating. I'll talk to you later.